Hello friends, I am Saroj Vishwas, gold medalist, first rank holder of 1994 batch in engineering stream of all the colleges affiliated to University of Mysore during that period. A B in civil engineering from National Institute of Engineering Mysore, a M.Tech in structural engineering from Indian Institute of Technology, Delhi, that is IIT Delhi, a Sun certified Java programmer, Sun Microsystem USA. I have more than 25 years of professional experience in designing building structures and allied subsidiaries. I invite you all to learn with me how to design building structures using commercially available structural softwares with the help of some manual computation as and when needed. In these sections, we'll continue with the primary loads. This section will cover the wind load cases. So we must understand the sign convention followed in wind load coefficient provided by the code. See, the coefficient provided in the codes are external pressure coefficient and the internal pressure coefficient. So anything that has a positive sign, that means the pressure is toward the surface, and any coefficient that has a negative sign means pressure is away from the surface, that is, it shall be a suction. The code divides the entire country into different basic wind zone. It has given a figure like this, figure of our country in this form with basic wind zone regions. So to arrive at design wind pressure, we have to consider basic wind speed, the risk coefficient or the probability factor, the terrain or height factor, topography factor, important factor for cyclonic region, wind directional factor, area averaging factor, and combination factor. Let us now compute the wind pressure. The length of the building is given as 12 meters. The width of the building is given as 12 meter. Eave height, including the plinth height, we have assumed as 450 mm. Works out to be 6.95 meter. Basic wind speed as per IS 875 part 3 for Delhi NCR region is 47 meter per second. So K1 is the design probability factor. For 50 years of life period, it shall remain 1. K2 is the terrain or height or structure factor. So if you go by code, it works out to be 0.91 for category 3. In most of the design situation, you will encounter category 3. Then K3 is the topography factor. That's actually what is the slope of the terrain. So we can consider flat slope for this. The K3 coefficient works out to be 1. And the K4 is the important factor for cyclonic region. So our region, that is Delhi NCR region, is away from the coast, so we do not need to consider it, so it shall remain 1. Then there are certain other parameters that we have to consider while arriving at design wind pressure. So this is KD, KA and KC. KD is wind directional factor, KA is area averaging factor, and KC is combination factor. So KD may be taken as 0.9 for building structure. KA is 0.9 for a bay area between 10 to 25 square meters. So our bay area also to be 4 into 3.25, 13 square meter. Even if we go for the Gavilan site, that will also remain within 25 square meters. So KA we can take as 0.9, and KC may be taken as 0.9 when the roof is subjected to pressure or internal pressure is suction, or vice versa, that is internal pressure within the building. So accordingly, we have worked out PD. PD comes out to be 0.8. Now reduction factor for building less than 10 meter height, we can reduce it by 20%. So reduction factors out to be 0.8. So PD works out to be 0.64 kilonewton per meter. While working out PD, we must remember PD should not be less than 0.7 PZ. So we have already worked out PZ as 0.6 into VZ square, 1.098 kilonewton meter square. So accordingly, that PD shall be arrived at. We shall assume our building is enclosure is is partially enclosed. The percentage of opening between 5 to 20%. So since this is the office area's mezzanine floor, so it will have lots of windows. So obviously for this building, it might percentage of opening might be well within between 5 to 20%. So it cannot go below 5% for other type of PEB watershed where the internal pressure coefficient is taken as 0.2. So for our case, it shall remain plus minus 0.5 internal pressure coefficient. Then you have to calculate H by W and L by W. H is the height of the eave, L is the length of the building, and W is the width of the building. According to that, we have to take the pressure coefficient from table 5. So table 5 is given, and we have put the pressure coefficient from the table 5 as per H by W and L by W. So these are the values. So these are the pressure coefficient, external pressure coefficient. Then pressure on the roof. We have taken a PVA structure with our roof slope is 1 in 10. So the roof angle works out to be 5.7 degree. This is the roof angle. For 5.7 degree interpolating, we get 0.93 between 0.91 and 1.1. Then GH 0.6, easy 0.7. So for what constitutes EF, GH, EG or FH area, you should refer to code there. Code has divided the roof area in four parts. So this is how the code has defined this roof area, E, F, G, H, and these the shaded part are the area where wind pressure is more and it is localized. So for our building, we are not considering it, but for area which are prone to cycle, we should also consider this local wind pressure. So as of now, for our building, we are not considering it. So we have this external pressure coefficient for roof. Now we have to calculate how this works out, how the pressure has to be worked out for each incidence angle of roof. So see, there will be 4 incidence angle for this is the direction when the wind is acting at 0 degree. This is the direction when the wind is acting at 180 degree. This is the direction when the wind is at 90 degree. This is the direction when the wind is acting at 270 degree. Accordingly, we shall work out our wind load cases. There will be one set of cases with positive internal pressure and the other set of cases with negative internal pressure. Now we must understand how these wind pressures are computed for a structure. So this is a rectangular shape. So I have found many of my friends to find it difficult to understand how the wind pressure is computed. So I'll explain it here as so that you are able to understand in a effective way how the wind pressures are actually calculated. Now let us try to understand how the wind pressure is calculated. It depends on the external pressure coefficient and the internal pressure coefficient. First set, we shall consider internal pressure coefficient to the positive. So if you see, this is our wall A, this is our wall B, this is our wall C, and this is our wall D. Now we have 0.7 for wall A, so it has a positive sign. So positive means towards the wall. So our external pressure coefficient shall act towards the wall. Then for wall B, it is minus 0.25. Minus 0.2 minus sign indicates that it shall be away from the wall. So this case is, this wind load is away from the wall. Minus, because this has a minus sign. Now come to wall C. Wall C has a minus sign, minus 0.6. So minus means away from the wall. And wall D also have minus 6, minus 0.6. So that means this is also away from the wall. So we have 0.7 towards the wall, plus 0.7 means toward the wall, minus 0.25 means away from the wall, minus 0.6 means away from the wall, minus 0.6 in wall D means away from the wall. Now let us come to internal pressure coefficient. Now this is 0.5 plus 0.5 plus 0.5 means the internal pressure shall act towards the wall along all the directions. So this direction also it is towards the wall. This direction also it is towards the wall. This direction also it is towards the wall. So now having written down the directions of positive pressure as well as having written down the values and directions of external pressure coefficient and internal pressure coefficient, we should now work out the effective coefficient in each direction. So now it will be not according to the sign convention, it will be as per the global direction. So we have x direction in STAAD and z direction in STAAD this way. So now we have to consider global direction, no more consideration of whether it is towards wall, whether it is away from the wall, while we'll compute the effective coefficient, algebraic sum of the coefficient. So we have in wall A .7 in this direction, minus 0.5 opposite to x direction. So we are considering x positive as this direction and z positive in this direction. So 0.7 is positive, 0.5 is opposite to x direction, so minus point. So this has minus 0.5. So effective pressure coefficient on wall A in the direction of x is 0.2. Now come to wall B. Now see, 0.25 is in the direction of positive direction of x. Again the internal pressure coefficient, this is also in the direction of positive x. So 0.25 plus 0.5, it works out to be 0.75. See, both internal pressure and external pressure is 0.5 and 0.25. Both are in same direction. So that is why we have added it. Whereas in wall A, 0.7 is in positive x direction and 0.5 is in negative x direction. So we are deducting 0.5 from 0.7. So we are getting net effective pressure coefficient as 0.2. Similarly, if we come to wall C, internal pressure coefficient 0.5 is along negative z direction. So we'll put 0.5 as minus. Again, 0.6 is also negative z direction. .6 is also negative z direction. So this together works out to be minus 1.1. We have not written the sign here in this Excel sheet because the arrow itself, this arrow itself is indicating what is the direction, net direction of the wind pressure. Similarly, come to wall D. We have 0.5 in positive z direction. Then we have 0.6 also in positive z direction. So our net pressure coefficient is 1.1. Now multiplying this net pressure coefficient with the design wind pressure, we get what is the actual pressure this all will be subjected to. Now let us come to the roof part. See, we have the external pressure coefficient as 0.93 and 0.6, and internal pressure coefficient is positive. That is also that will be towards the surface. Positive means surface, towards the surface. If you see the roof pressure, this is minus 0.93 and minus 0.6, minus 0.93 and minus 0.6. So that means they are away from the surface. Surface is what? Or roof, because they have minus. So they both have the same direction. So they will be added up. So 0.93 plus 0.5 works out to be 1.23. 0.93 for this roof, the effective pressure shall be 0.93 plus 0.5, that works out to be 1.43. This 1.43 shall be multiplied with design wind pressure to get this actual pressure that the roof will be subjected to. Similarly, for this 0.5 or 0.6, that is external pressure coefficient plus internal pressure coefficient 0.5, this works out to be 1.9, 1.1. So again multiplying with this, we get this value. So now let us see how the pressure coefficient will be calculated when this will become negative pressure. This is negative interior pressure, means pressure is away from the wall along all directions. So these directions, these directions, these directions, these directions, and our external pressures or external pressure coefficient remain as before: 0.7, 0.25, 0.6. Now let us come to the roof. Global y direction of STAAD positive is y. So if we see 0.93 and 0.5, 0.5, 0.93 is positive and 0.5 is in opposite direction of negative direction of y. So effective pressure coefficient works out to be here 0.43. For this part 0.6, then internal pressure coefficient is along the negative y direction. So this is this is 0.5. So this value works out to be so this is along the global y direction of STAAD. I hope with this we have been able to understand how the wind pressure and magnitude and direction of wind pressure has to be worked out. Now let us come what is to be applied on STAAD Pro. Now this is the case which has to be applied to STAAD Pro. This is the case where the wind incident is along 0 degree positive internal pressure. So we had already worked out the pressure. So let us go for take a look at the wall A. So we have 4 member. If you see the tributary width of each of this column, this is 4 by 2 is equal to 2 meter. For this column, from both sides it will get the tributary area. So 4 by 2 plus 4 by 2, tributary width is 4 meter. Again for this column the tributary is 4 meter. Again for this column only half of this area, that is 2 meter. Now we had already worked out the pressure 0.13 kN per meter square. So 0.13 into 2 is equal to 0.26 kN per meter of UDL will be applied to this column in global x direction. Again 0.13 into 4, 0.52 will be applied in global x direction for this column. For this column as well as same. For this column again 0.26 kN per meter. So from this figure you can work out, you can understand how this wind pressure are to be applied on STAAD Pro. So we already had 0.7 as wind pressure in this direction, 0.7. So 0.7 into for this column the tributary width is 3 meter. For this column it will become 6 meter, half from this and half from this. Similarly for this raptor, for gable raptor, the tributary width will be 2 meter. So 0.7 into 2 is equal to 1.4 kN per meter. 0.7 into 2 is equal to 0.7 into 4 is equal to 2.8 kN per meter. So this is how the loads to STAAD Pro software has to be applied. So let us open the STAAD Pro software now to apply all this load. Now let us come to discuss how this wind load which we have worked out are to be applied in a structural model, what that has been developed in STAAD Pro. The figure on the right side, this figure shows what we have worked out for wind with 0° incidence. The figure on the left side shows how these loads are to be applied on a STAAD Pro model. So if you see, for this we have to take into consideration of the contributory width for each of the structural member. So for this column, the tributary width is half of this span, that is 4/2. This span is 4/2. For this column, half from left side and half from right side. So this works out to be 4 meter. For this column again, half from left side and half from right side. So this works out to be 4 meter. For this column, half from right side. So this works out to be 2 meter. Similarly for gable rafter, this is half 2 meter. For interior rafter, half from left side and half from right side. So tributary width is 4 meter. So we have, from the wind load calculation, on the wall A, the wind load magnitude is 0.13 kilonewton per meter square. So what is the load to be applied on this frame? This is 0.13 into 2 meter, that is the tributary width, is 0.26 kilonewton per meter. Similarly for this and this frame, 0.13 into tributary width, that is 4, is equal to 0.52 kilonewton per meter. Similarly, if we go to the rafter, we see the magnitude of load we have worked out is 0.91 kilonewton per square meter. So tributary width of this gable rafter is 2 meter. So 0.91 into 2 is equal to 1.82 kilonewton per meter. Similarly, if you see, the tributary width of this interior rafter was 4 meter, half from this side and half from this side. This is 4 meter. So 4 meter multiplied by 0.91 is equal to 3.64 meter. Same is here, and again same is for the as for the gable rafter on the left side. Similarly, on the wall B, the magnitude of wall load is 0.48 kilonewton per meter. So on this column at the gable end, it is 0.48 into 2 into 0.96. 2 is the tributary width of this column. Similarly, if you see, this is wall C and this is wall D. So for wall C, the tributary width is same as this, 6/2, half of this. 6/2 is equal to 3 meters. So 3 meter into 0.7. This is wall C, 0.7. So 0.7 to 2.1 kilonewton. So it is in negative direction of the Z. Similarly here, 0.21 kilonewton meter, it is in the positive direction of Z. Similarly, for this column, tributary width is 6 meter. So 6/2 plus 6/2, 6 meters the tributary width. So 0.7 is the magnitude of the wind pressure on wall D. This is wall D. So 0.7 into 6 is equal to 4.2 kilonewton per meter. So with this we have worked out the UDL, uniformly distributed load in running meter, that has to be applied on each structural member that will be resisting the wind load. So now in this way we can calculate for all the 8 cases that constitute the wind loading. Wind 0, positive interior pressure. Wind 180, positive interior pressure. Wind 0, negative interior pressure. Wind 0, negative interior pressure. Wind 90, positive interior pressure. Wind 270, negative interior pressure. Wind 90, sorry, this is positive interior pressure. Wind 90, negative interior pressure. Wind 270, positive interior pressure. So we have 8 cases: 1, 2, 3, 4, 5, 6, 7, and 8 cases. So if you see, wind load case 2 is exactly opposite of wind load case 1. Similarly, wind load case of 4 is exactly opposite of wind load case 3. So wind load case 6 is exactly opposite of wind load case 5. Wind load case 8 is exactly opposite of wind load case 7. So that is why we have considered the positive interior pressure in first group, then negative interior pressure in first group, positive interior pressure in first group, then negative interior pressure in first group. This will help us when we have already assigned the load in the STAAD Pro. We can click on each of this load and just to check up whether the wind 180 degree is opposite to wind 0 degree positive. Now let us go to the STAAD Pro model again. So we have the STAAD Pro model on the left side and the wind load for 0 degree incidence of wind is on the right side. Now let us go to general, then select load cases, expand the load cases. We select wind 0 degree positive, click add. The first load case we shall have assigned for all A. We have in GH direction 0.21 kilonewton meter. Let us add it. 0.21 kilonewton meter, add. Then we have 0.52 kilonewton per meter, add. Close. So 0.21 kilonewton per meter load will be along the columns at the gable end, assigned to the selected beam, assigned. So this has been assigned. Then 0.52 at this column at interior, so assigned. Now let us go back to the wind load 0 degree again. Now add this to load. This is 1.9, 0.96 and 1.92. That is for all B. Add member load in GX direction. This is X direction of Z. STAAD Pro 0.92 at 1.92 at. So let us assign them. 0.92 will be on gable columns. Select the gable columns or corner columns. Assign to the selected beams. Then 1.92, select the interior columns. Assign. Then you have to go to wall C. In wall C we have 2.1 kN per meter in minus negative Z direction of STAAD Pro, 4.2 kN per meter and 2.1 kN per meter. So let us add this again. Go to wheel load 0 degree, add member load minus 2.1 in global GZ direction, add, then add minus 4.2, add. So we have this load on these columns, assign, and 4.2 on this column. This is for all C. Assign, yes. Then let us go to wall D. In wall D again it is 2.1, 4.2, but this is along positive Z direction. So let us add again this load, member load minus 2.1, sorry, positive direction 2.1 in global Z direction, add, then 4.2 in global Z direction, add. 2.1 for this corner column, assign, then 4.2 for this interior column of the gable, assign. So we have now assigned the wind pressure on all the full load. Now we have to assign the uplift on the raptor. So let us go to select by group name. The raptor and along with that cantilever also. Okay. View, selected object. Now see, the wind pressure always act normal to the surface. So the raptors are inclined. So if we take global Y direction, then the application of wind load will not be proper. So for this, the way out is to take local axis of this raptor. So we have 0.91 into 2, 1.82, then 0.91 into 3.4 is 3.64. So let us add this wind uplift, member load. Now we have to select local Y axis. So 0.91 added, then sorry, this is, let us delete this node. This is not 0.91, delete. Okay, go again, add member load 1.82. It is in positive Y direction, in positive local Y direction. Add, then 3.64, add. 1.82 will be on the global raptor on the wall side A. This is wall side A. Assign to the selected view. Okay, assign. Now see, these wind load directions are perpendicular to these raptors. Then now let us go to the site on the raptor on the side wall B. This is side of wall B. This is leeward side when the wind is acting at 0 degree to the structure. So let us again add the wall. We have 0.96 and 1.92. 0.96 and 1.92. Let us add this load. Add again in local y direction 0.96. Add 1.92. Add 0.96 on cable raptor. Assign and 1.92 on interior raptor. Assign. Now let us see the whole structure view. Let us open the loading box again. Select the wind load case. Click on it. Now all the wind loads have been applied. You see the similarities between what have been calculated in the 3D view and what we have applied. Let us now open the STAAD Pro editor to apply all the other 7 wind load cases. Because if we apply the way we have applied for the first load case, it will be time consuming. So the faster way of assigning wind load is to use STAAD Pro editor. We should actually use STAAD Pro editor as much as possible. That makes the modeling process faster. So let us open the STAAD Pro editor. Scroll down to load number 21. So let us first classify with comment line which load has been applied to which wall. The first 2 load cases we know is wall A. Let us put a comment line, wall A. Then the third and fourth are wall B. Then fifth and sixth are wall C. Seventh and eighth are wall D. Now this is the wind load. First 2 cases are the load that has been applied on the raptor on wall side A. So roof on wall side A. Roof on wall side B. Now we shall copy this load case number 21 and use it to generate load number 22. That is exactly opposite of load number 21. So copy this, let us paste it. Now let us see what happens in load number 22. You See, load 22 is exactly opposite of load 21. So 0.48 has come to wall A in opposite direction. 0.13 has come to wall B opposite direction. 0.91 is now on this 0.9 on has now gone to this place, and the 0.7 has come the wall side A. So this 0.21 becomes 0.92, 0.52 becomes 1.92, and then 0.21, 0.52, 0.21 and 0.52. Wall C and wall D remain same. Now this 0.96 and 1.92 goes here. 0.96, 1.92. The other value is 1.82 and 3.64. 1.82 and 3.64. The next load case is load 3, wind 0 degree, negative CPI. Now for this negative CPI we see one wall A 0.77 kN per meter square, but on wall B it is in negative x direction. So let us again go to load number 21, copy it, paste it below load number 23. Load case 23 is wind 0 degree with negative CPI. 0.77 kN per meter square is on wall A, and 0.16 kN per square meter is on wall B, but it is in negative direction. So let us go back to load number 21, copy this, copy and paste it below load number 23, Control B. So 0.77 into tributary width of corner column is 2 meter, 1.54. Tributary width is 2 meter, so 0.77 into 2 is 1.54. Then tributary width of intermediate column is 4 meter, so 4 into 0.77 is equal to 3.08. Let us come to load number 23A. Now load number 23 is wind 0 with degree with negative CPI. So on wall A the pressure is 0.77 kN per square meter. On wall B it is 0.16 kN per meter square, but it is negative x direction. So let us go back to load number 21 again. Copy all the member loads, paste it below load number 23. So 0.77 for the corner column, 0.77 into tributary width 0.2 meter, 0.77 into 2 is equal to 1.54. So for the corner column it is 1.54 in positive x direction. Then for intermediate column 3.08, that is to 4 meter tributary width into 0.77 is 3.08. Now in wall B the loads are in negative x direction. 0.16 into 2 is equal to 0.32, so minus 0.32. Then for intermediate columns 0.16 into 4 meters, tributary width of intermediate column 4 meter. So this works out to be 0.64 in negative x direction. For wall C 0.1 into 0.06 into 3 meter. For corner column, that is 0.18. For intermediate column at gable end, it is 0.3. 6 meter into 0.06 is equal to 0.36. Now this will be also have same value but in positive z direction. Now roof on the wall side A, 0.27 into 2. For gable side rafter, that is 0.54. And 0.27 into 4 is equal to 1.08. For intermediate rafter, so for intermediate rafter, 0.27 into 4, 4 is the typical width, 1.08. Then for the rafter on wall side B, 0.06 into 2 is equal to 0.12. From 0.6 into 4 for intermediate rafter, 0.24. So again, the load case number 24 will be opposite to 23. So let us copy load number 23 below load number 24. Now this 0.32 the load number 24 is just opposite of load number 23. See, the 0.77 has gone on all B is direction has 10 direction is opposite to 0.77 on LA on all A, but it has same direction as it was there in load number 23. So the greater force has gone on the side B and the smaller force has come on the side A. Similarly, the load on the rafter also had changed their side. So we had pasted load 23 below load 24. Now we have to change their value. So this become 0.32. This becomes 0.64. And then 1.54 and 3.08. 1.54, 3.08. See, it is in negative x direction. Negative x direction. So on all B, wall C and wall D remain same. On the rafter, the side changes 0.12, 0.12 and 0.24. Then 1.82 and 1.08. So this should be actually 0.27 into 2. We did not change it. 0.27 into 2 is equal to 0.54 for load case 3. So load case 23 is something like this. 0.27. So 0.27 and then 0.27 into 4 is equal to 1.08. 1.08 is okay. 0.27. So this is 0.27 for load. For this one, on all side B, 0.27 into 2, 0.54. And this will be 1.08. See, it has changed the size. From here it was on all side A, here it has come to on the all side B. Our next load is load 25, wind 90 degree, positive CPI. This is our case. Wind 90 degree with positive CPI. So values are here. So we'll just take this load case 24, copy it, and paste it below load case 25. Now see, one wall A and wall B, 0.64. 0.64 into 2 equal to 1.28. In negative x direction, then 0.64 into 4 minus 2.56. In negative x direction, then this will be in positive direction, same value, 1.28, 2.56. Now on wall C, it is in positive z direction, 0.13 into 3 meter is equal to 0.39. And 0.13 into 6 meter is equal to 0.78. All D, it is 0.48 km per meter square. So for corner column, 0.48 into 0.3, 0.48 into 3 meter tributary with the corner column, 1.44. Then 0.48 into 6 meter tributary with Gable intermediate column. Tributary with the Gable intermediate column is 6 meter. So 0.48 into 6 is equal to 2.88. The values on the left on both all A and B remain same. So 0.83 into 2 is equal to 1.66. .83 into 4 is equal to 3.32. This will also become same, 1.66, 3.32. So this completes our load case number 25. Load case number 26 will be exactly opposite of this. Wall A and wall B remain same. Wall C, now this become 1.44 but in negative direction, minus 1.44 and minus 2.88. Then this becomes 0.39 and 0.78 in negative direction, minus 0.39, minus 0.78. The roof raptor loading remains same. Now let us come to load 27 wind 90 degree with negative CPI. Now for on this thing, see, code actually defines leeward side, windward side and leeward side. So one has a greater uplift, the other has a greater lesser uplift. So we should actually consider the lesser one, because at time it could create pressure and add to dead and live load. So during negative pressure we should consider the lesser value or uplift or the pressure that is being created. So for this is wind 90 degree. Wind 90 degree with negative interior pressure, the pressure works out to be like this. So let us copy this load member, load case 26, copy it here. All A and all B is 0, it is 0. So actually we should not put 0 0 because we might have to, this will eliminate these load cases from STAAD Pro automatically if we put 0. So it's better to put some value which tends to be 0, so that in future if we require to change it, we can change it, we do not have to write it all over again. So we are putting 0.001, so it is almost 0. Then one wall C, it is 0.77. In positive z direction, 0.77 into 3 meter is equal to 2.31. Then 0.77 into 6 meter is equal to 4.62. And on wall D it is in negative z direction. So 0.16 into 3 is equal to minus 0.48. The next value will be double. 0.48 into 2 is equal to 0.96, or 0.16 into 6 is equal to 0.96. The roof pressure is 0.06. So 0.06 into 2 is equal to 0.12. Point 0.06 into 4 is equal to 0.24. And this will also remain same, 0.12 and 0.24. Now load case 28, 270 degree, it will be opposite of wind 90 to load case 27. Let us copy it, paste it below load number 28. So wall A and wall B remain same. So this become 0.48 and minus 0.48 and 0.96. The direction remains as before, and then this becomes 2.31 and 4.62. 2.31 and 4.62. Because now on the wall D the pressure is towards wall D, so it is in negative z direction. The roof pressure remains same, roof pressure or uplift remains same. So let us go through all the load cases if some typographical mistake is there. Let us save it and close the editor. Save and close. The STAAD graphical user interface comes up. We go to load. Just check if everything is okay. So our getter load in all B, in load 22. Getter load is in all A. Actually, this should be in negative direction. We probably forgot to change it. That is why we should check it once in the graphical user interface. So let us edit it. 0.92 change 1.92 minus 1.92 change edit minus 0.21 change close minus 0.52 change. So here the wall is in positive x direction, here is load is positive x direction, here is the load is negative x direction. So load 21 and 22 are okay, they are opposite to each other. Now let us check load 23. 0.92 load 23 is here, 1.54, then 3.08 in positive x direction, load 24, 3.08 in negative x direction. So this also seems to be okay. Then let us go to load 25, 1 point. Let us see the load on wall C, on wall D. Wall D 2.28, 2.88, and in load 26, what is on wall C? 2.88. They are opposite to each other directions. So then comes to load 27 on wall C, 4.62, and load 28. What is on wall D? Minus 4.62. So they are opposite to each other. So our wind loads are okay. So checking of wind load is over. With this, we come to the end of this section. In next section, we shall discuss load combination. Till then, let us meet on the next section on load combinations.